Okay, let's unpack this. I want you to imagine a single document. It's just 10 pages long.
Right.
It was uploaded to a server back in 2017, probably by some guy in a t-shirt, drinking stale coffee. And yet that 10-page PDF is effectively the constitution, the blueprint, and maybe even the big bang of the entire modern AI era, all rolled into one.
It's not an exaggeration at all. If you look at the landscape of technology today, I mean, here in 2026, almost everything important AI stems from this one moment.
It's a dividing line.
It is. There is before this paper and there is after this paper, period.
We are, of course, talking about the research paper titled "Attention is All You Need" by a team at Google. And I was looking at the stats you pulled for this deep dive. This is actually insane.
It's mind-boggling.
As of 2025, this paper sits in the top 10 most cited papers of the entire 21st century.
Right. Over 173,000 citations. And, to put that in perspective, a truly groundbreaking paper in, say, biology or physics is lucky to get a few hundred citations.
A few hundred.
This didn't just nudge the field. It completely reinvented the physics of how computers process information.
And that's exactly why we're here today. Because everyone knows the brand names. We all know ChatGPT, Gemini, Sora. We use them, we talk to them, we let them write our emails.
Sure, they're household names.
But almost no one understands the engine underneath the hood. Today, we are going to deconstruct the transformer.
Which is the architecture that was introduced in this paper.
Exactly. Our mission is to move past the buzzwords. We're going to look at the history, the technical details, to really understand mechanically why this specific architecture changed everything.
And we should probably say we're going to get into the weeds a little bit. We're going to talk about vectors and matrices.
But we promise to keep it English.
We'll keep it grounded. But you can't really understand the revolution without understanding the machine itself.
So to appreciate the aha moment, we have to understand the before times. Take us back to, say, pre-2017. If I wanted a computer to translate a sentence from English to German, how did it do it? Because we had Google Translate before 2017.
We did, but it was clunky. The dominant technology at the time was something called recurrent neural networks, or RNNs.
Okay.
And specifically a more advanced version called LSTMS, long short-term memory networks.
Long short-term memory, that sounds like a contradiction.
It was a brilliant solution for its time, designed to solve a very specific problem, memory. But here was the massive constraint. It was strictly sequential.
Sequential, so one after the other.
Exactly. Imagine you're trying to read a book, but you can't look at the whole page. Instead, you have to look at the text through a tiny slit in a piece of paper that only reveals one word at a time.
Okay, I'm picturing that, like reading a scroll.
You read the first word, you process it, you try to remember it, then you slide the slit to the second word, you process that, add it to your memory of the first word, then the third. You are forced to move left to right, step by step by step.
So if I'm the computer, I literally cannot look at word number 5 until I have finished processing word number 4.
Precisely. And that created two massive problems that were basically strangling the entire field of AI.
Okay. What was the first?
Speed. You couldn't parallelize the work?
Hold on, let's dig into that. Parallelize is a big word. Why couldn't I just buy 1,000 computers and have them all read the sentence at the same time?
Because of the dependency. Think of it like a relay race. Runner B cannot start running until runner A physically hands them the baton. It doesn't matter if you hire Usain Bolt for the second leg. He just has to stand there and wait.
So if I have a really long sentence or a whole book, the computer's just chugging along one word at a time.
Exactly. Modern GPUs, graphics processing units, are designed to do thousands of things at once. But RNNs forced them to do one thing at a time. It was incredibly inefficient.
And the second problem?
The second problem was even worse. It's a concept called the vanishing gradient.
The vanishing gradient? That sounds like a horror movie title.
It's the horror movie of linguistics, basically. It just means information loss. Since you're processing strictly in order, by the time the model gets to the end of a long paragraph, it tends to forget what happened at the beginning.
Kind of like a game of telephone.
A very good analogy. The model tries to cram the context of the first word into this little package of numbers, a state vector. Pass it to the second word, modify it, pass it to the third.
And by the end?
By the time you're 50 words in, the signal from word number 1 is barely a whisper.
So if I have a sentence like, the girl who lived in the blue house down the street and liked to eat apples went to the store. By the time the computer went to the store, it might have forgotten who the girl was.
Exactly. It knows someone went to the store, but that connection, that thread back to the subject, is weak. The context gets totally diluted in the bottleneck. The world needed a way to process the whole sentence at once.
And that brings us to the heroes of our story. The team behind Attention is All You Need.
Team Transformer, as they apparently call themselves.
It was 8 scientists at Google: Ashish Vaswani, Noam Shazir, Nikki Parmar, Jacob Uskarite, Leon Jones, Aidan Gomez, Ugas Kaiser, and Ilya Polasukin. And here's a fun fact I found in the notes.
Oh, yeah.
They contributed so equally to this thing that the order of their names on the paper was randomized.
Which is incredibly rare in academia. Usually the first name is the star and the last name is the boss. But here, it really was a collective mind meld. They were just jamming on ideas.
And looking at where they are now in 2026, the band has definitely broken up.
Oh, completely. Every single one of them left Google. They all went on to found their own huge startups like Cohere, Character.ai, Near, or join other major players. It's basically the PayPal mafia, but for this generation of AI.
But before they split up, they had to name this thing. And for a paper that changed history, the naming process was surprisingly casual. Transformer.
Yeah, Jacob Uskarite just liked the sound of it. He thought it sounded powerful. In fact, our source material says that some of the early design documents actually featured characters from the Transformers toy franchise.
No way.
Yes. Optimus Prime and Megatron were apparently in the margins.
And the title of the paper itself, Attention is All You Need.
A nod to the Beatles. All you need is love.
I love that. It adds a bit of personality to what is some very dense math. But the title was also a huge controversial claim. Attention is all you need. They were saying, hey, all that recurrent stuff, all those LSTMs we've been using for a decade.
I throw them in the trash.
Yeah.
Is a radical hypothesis.
Yeah.
Jacob Uskarite suspected they could just ditch recurrence entirely. And our source notes that even his father, who's a famous computational linguist, was skeptical. He basically told his son, you can't just ignore the order of words. Language is order.
But they did. So let's get into the machine. This is the part everyone struggles with. How does the transformer work if it doesn't read one word at a time?
It uses a mechanism called self-attention. So instead of that slit-in-the-paper approach, imagine looking at the entire page instantly. The model looks at every single word in the sequence at the same time, and it calculates how much attention each word should pay to every other word.
Okay, let's unpack that with an example. Let's use the sentence. The animal didn't cross the street because it was too tired.
Great sentence. Okay, when a human reads that, we get to the word it because it was too tired, and we instantly know that it refers to the animal.
Right, because streets don't get tired.
Exactly. We use common sense and context, but a computer doesn't have common sense. It just has numbers. So self-attention allows the model to connect the word it really strongly to the word animal and very weakly to the word street. It builds a web of relationships.
Okay, but how? The paper talks about this query key and value system, the QKV. This is usually where people's eyes glaze over. I want you to explain this so my grandmother would get it.
Challenge accepted.
Oh.
The best analogy is a library retrieval system.
Okay, I'm in a library.
Imagine every word in that sentence is a person in a library. Let's take the word it. It is trying to figure out what it means. So it creates a query. Think of the query like a sticky note on its forehead that says, I am a pronoun looking for a noun that can get tired.
Okay, so the query is the intent. What am I looking for?
Exactly. Now, every other word in the sentence, animal, street, cross, is standing there holding a book. And on the spine of that book is a label. That label is the key.
So the key is like the description of what that word offers.
Yes. The word street has a key that says, I am a rigid paved surface. The word animal has a key that says, I am a biological entity that experiences fatigue.
I see where this is going. My query, looking for something that gets tired, scans all the keys.
And it finds a match. The query for it meshes perfectly with the key for animal. That mathematical match, it's called the dot product, creates a really high score. It's a high compatibility rating. It clashes with street, so that gets a low score.
Okay, so I found my match. I know it belongs to animal. What happens then?
Once you find the match, you take the book off the shelf and open it. The information inside, the actual meaning, the essence of that word is the value. You then absorb that value. So now the representation of the word it is updated with the value from the word animal.
That is actually really helpful. So instead of just next word, every word is constantly querying every other word to see, hey, are we related? Do you have context I need?
Precisely. And it happens all at once. Animal is querying tired. Cross is querying street. It's like a massive simultaneous cocktail party where everyone is talking to the people most relevant to them.
Now, in the paper, there's a scary-looking formula. The attention QKV equals a bunch of math.
Right, we won't read the calculus, but the concept is just what we described. You multiply the query and the key to get a raw score. Then you use a function called softmax. And think of softmax as like the referee. It looks at all the raw scores and turns them into clean percentages. So it's like you are 90% related to animal, 5% to street. Exactly. And 5% to cross. Simple enough. But then they add another layer, multi-head attention. Because apparently paying attention once isn't enough.
Right.
Think of it as having multiple pairs of glasses or maybe multiple agents looking at the same sentence. If you only have one head, you might only focus on who is doing what action.
But language is more complex than that.
Exactly. So the transformer uses multiple heads. One head might be tracking grammar-like subject-verb agreement. Another head might be tracking gender-connecting king to he. Another might be tracking tone or style.
So it's like a committee. One person checks the grammar, another person checks the definitions, a third checks the context.
And they all report back at the same time. This creates a much richer, much more high-definition understanding of the sentence than an RNN ever could.
Okay, I'm with you on the mechanics, but here's the part that still bothers me. You said the model reads the whole sentence at once, parallel processing.
Yes.
But order matters. The dog bites the man is a news story. The man bites the dog is a viral video. They're totally different. If I throw all those words into a bag at the same time, how does the model know who bit who?
This was the biggest criticism Jacob Uskereit's father had. You've lost the order. And since they ditched recurrence, they needed a way to artificially stamp the order back onto the words. This is the concept of positional encoding.
And the source says they used sine and cosine wave functions. Wait, hold on, sine waves. Like from an oscilloscope. Why would a language model need a wave function? That sounds like physics, not grammar.
It does sound weird. But just think about a wave. It repeats, but it changes its values slightly at every single step. Imagine you have a color gradient that shifts very, very slowly from, say, red to blue across the sentence. The first word is pure red. The last word is pure blue. And every word in between has a slightly different shade of purple.
So the word carries its meaning, but it also carries this little color that tells the model where it sits in the line.
Exactly that. The sine and cosine waves are just a mathematical way to generate those unique colors or fingerprints for every position. So when the model looks at the word man, it sees the meaning adult male, but it also sees a mathematical stamp that says position 3.
So even though it processes everything at once,
That stamp preserves the sequence.
that feels like a hack. A brilliant hack, but a hack.
In a way, it is. But it was an incredibly elegant solution that didn't require sequential processing. It gave us the best of both worlds, the speed of parallel with the structure of order.
So we have self-attention, the cocktail party. We have multi-head attention, the committee. And positional encoding, the timestamps. That's the engine. Now let's talk performance, because the whole point of this was speed.
And this is where the numbers just get staggering. The source material notes that the base models were trained on just 8 NVIDIA P100 GPUs.
Only 8. In today's world, we talk about clusters of 100,000 GPUs. 8 sounds like a gaming PC setup.
It was so efficient. The base model took only 12 hours to train. The big model took 3.5 days.
Okay, compare that to the before times. How long did the old stuff take?
The source mentions that the previous Google Neural Machine Translation System took 9 months to develop, and the statistical approaches before that, 10 years of engineering.
So we went from years to months to 3.5 days.
That is the power of parallelization, because you aren't waiting for the scroll to unwind anymore.
You can just throw more compute at it, and it actually works. You can scale it.
Exactly.
And originally, they just wanted to translate languages, right? The paper focuses on English to German. They didn't know they were building the foundation of HEI.
That's the beautiful irony. They were just trying to get a better translation score. But they saw these early signs that this wasn't just a translator. The team decided to throw a curveball at the model. They tried it on something called English constituency parsing.
Which is what?
It's rigorous grammar analysis, identifying noun phrases, verb phrases, the whole sentence tree structure. A totally different task from translation.
And they didn't even tune the model for it.
Nope, they just ran it. It worked brilliantly.
And didn't they have it write a Wikipedia article?
It did. As a test, they had it generate a fake Wikipedia article about transformers. And it wrote this coherent, factual-sounding article.
Dude, very meta.
It was a proof of concept. They proved this architecture could generate coherent text, not just swap words around. They'd built a general-purpose language engine.
Which brings us to the aftermath. The paper was published in 2017. what happened next is basically the history of the last decade.
It just triggered the AI boom. Almost immediately, you saw the evolution. In 2018, we got BERT from Google, which totally revolutionized Google search.
And then the generative pre-trained transformers.
The GPT series, yeah. OpenAI looked at this architecture and basically said, what if we just make it bigger? Much, much bigger.
The source notes that the sheer scale of the 2022 boom with ChatGPT was unexpected, even to the researchers.
Well, the architecture allowed for what we call quadratic scaling. Because it was parallel, you could just stack more layers, feed it the entire internet, and it just kept getting smarter. It didn't hit a ceiling like RNNs did.
But here is where it gets really interesting for me. I want to connect this for the listener who thinks, okay, cool text generator. It's not just text anymore. We call it a language model, but the transformer doesn't seem to care what the language is.
This is the multimodal shift, and this is key. See, the transformer treats everything as a token. A word is a token. But a patch of pixels in an image, that can also be a token.
Explain that. How is a picture a language?
Think about the query key concept again. If I have a picture of a beach, I have a patch of blue pixels at the top. That patch is a token. It queries the pixels around it. It asks, hey, am I part of a blueberry? Or am I part of the sky?
And the surrounding pixels reply, well, we are white and flicky clouds, and below us is an ocean.
So the blue pixel says, okay, I am sky. It uses the exact same attention mechanism to understand the image.
So that's why we have vision transformers, and that's why we have Sora creating video.
Exactly. Sora treats chunks of video as tokens. It predicts the next frame token, just like ChatGPT predicts the next word token.
And even biology. You mentioned AlphaFold.
AlphaFold changed the world of biology by predicting protein structures. It treats amino acids like they're words in a sentence. It uses self-attention to see how the protein folds up on itself. This amino acid attracts that one over there. It's just finding relationships in data.
It's incredible to think that a mechanism designed to translate the cat sat on the mat into German ended up solving protein folding and creating Hollywood-level video.
It really speaks to the universality of the architecture. Attention, the ability to weigh relationships between data points no matter how far apart they are, turns out to be a fundamental law of information processing.
So what does this all mean for us? For the person listening who isn't an AI researcher?
It means we've moved from a world of rigid, rule-based computing to a world of relationship-based computing.
Unpack that a bit.
Before transformers, computers were just very bad at context. They were literal. They were linear. You made a typo, they crashed. Now we have machines that can see the whole page at once. They can understand that a word or a pixel or a gene only has meaning in relation to the things around it.
It's a connector.
It's a universal connector. The transformer gave us a method to map the relationships between any set of data points. And that is why it is the engine of the 21st century.
It really is the constitution of the AI era. It defined the rules of engagement for how machines learn.
And we're still just seeing the early applications of that. Remember, the paper foresaw question answering, but I don't think even the authors realized how quickly it would scale to things like robotics and reasoning.
It's a good reminder that sometimes the biggest revolutions come from a 10-page PDF.
And a group of people willing to challenge the conventional wisdom. Remember, everyone was saying you need recurrence, you have to read in order, and they just said no. Attention is all you need.
I want to leave the listener with a final thought, something to chew on. We've talked about how the transformer moved us from sequential processing thinking linearly to parallel processing, seeing the whole picture at once.
Right.
It makes me wonder about our own brains. We tend to think linearly, we tell stories beginning to end, we read left to right. But the transformer proved that attention without strict order is faster and more powerful for processing data.
That is a deep thought.
Yeah.
It implies that linearity might actually be a bottleneck in our own cognition.
Exactly. If attention was all we needed to solve language, what other simple mechanism are we overlooking? Is there a creativity is all you need, or a reasoning is all you need? Paper just waiting to be written? What's the simple mechanic that unlocks that next level of intelligence?
If we find it, it'll probably be another 10-page paper that nobody notices at first.
And we'll be here to deep dive into it when it drops. Thanks for listening, everyone.
Keep learning.